And I feel very honored to give the first talk on this conference and start this wonderful topic and discussion. So I'll be talking about stellar populations and star formation history. And I will give you some background in the first half, and later on we'll show you a little bit of what we've been working on in Portsmouth on this topic recently. So this is not really an introduction anybody needs at this particular conference, but I think it's worth reminding ourselves that galaxy formation is a very, very complex process. We know the galaxies are growing out of primordial density fluctuations. Dark matter very likely is playing the key role there. But really, when it comes to understanding galaxy formation and the processes, there's lots of physics going on between baryons and dark matter, or baryons alone, that is very difficult to understand. And obviously, there's still a lot of work to do to really get all this physics knowledge about the formation of galaxies. And I think that's what we're all interested in, and that's why we are here today and this week. And one of the ways to address this, there are many, of course, but one of the ways what I'm talking about today is using to look at the baryon physics in galaxies of using stellar populations. Now, stellar populations are great because they keep the fossil record over the star formation history. So we're a little bit like archaeologists, that we are looking at star formation, stellar populations in galaxies, and try to put together the puzzle of how that stellar population or that entire galaxy has formed over the course of its in the universe. Obviously, that also, so that advantage also makes it really, really difficult, because to disentangle stellar populations of different epochs and disentangle them from all sorts of different effects, like, of course, metal enrichment effects, dust, star formation, and all sorts of things, we all know makes it really, really hard. One of the things I just want to this is a bit reverse engineering, tell you something about the result that has been found a while ago, that we have been leading and many people have been studying this area and found very similar things, is downsizing, which obviously has a very large impact on our understanding of galaxy formation. And by being able to tap into the fossil record of the stellar populations, we were able, and I will show you on the next slide a little bit how we did this and how people are doing this, but I want to anticipate the result here. One of the key results there, I think, was that through the chemical enrichment processes that we could measure in stellar populations, we realized that very massive galaxies must have had a very squeezed formation histories, forming their stellar populations on the shortest timescales, which, if you think of a hierarchical formation scenario, is immediately clear is quite challenging. So this kind of downsizing pattern is something that has been following the challenge of theory of galaxy formation for quite a while. And where this comes from is on the right-hand side of this slide, you can see this alpha to iron ratio, which is the alpha elements, light elements relative to iron that we measure, and that tell us something about supernova type 1a versus type 2 supernova contributions. And that then we can convert into a timescale of star formation. And there is this a very prominent relationship that has now survived over several decades, that the most massive galaxies have the highest alpha to iron ratio, and that means the shortest formation timescales. And you can see very nicely in this plot from the Eagle collaboration, where they reproduce observations that you actually you can reproduce those with some assumptions that are quite ad hoc. It's not yet about understanding the physics, but you can kind of make it work by doing something that resembles an idea of AGN feedback that shuts off star formation. But you can also see from the red dashed line that if you don't do that, take the models as they are, you will never recover this kind of relationship, this kind of downsizing pattern that we see in the galaxy population. So let me make that one step back. Now, or several steps back, really. Of course, the challenge of stellar populations in galaxies is that they are not resolved. And that's an example of a globular cluster. You can see the various stars. You can take a spectrum, a little bit as what you're used as a stellar astronomer to see. And of course, in galaxy populations, that's what we see for the same wavelength range. Of course, all the little features that we can use to derive very accurate parameters for stars, they are all washed out in a galaxy spectrum, simply because of the velocities of the stars in galaxies. And so a lot of work has gone into developing stellar population models that can actually describe this, and then that can use kind of, I don't want to say it's not deconvolving, but still try making best effort of extracting that information that is lost due to these velocity shifts. And one of the ways that we have started doing this about 20 years ago, and that's still the way it's being done, is to, when you want to look at various element abundances and metallicities that you vary in a model atmosphere, of stellar model atmosphere, you vary your element abundances and you look at the differential effect. This is what this equation here is supposed to show. So that's the main way of how we can actually understand how stellar spectra and then spectra of stellar population change when we change element abundances. And that's how we can kind of tap into this, even though much of the information is washed out in the observations. And that's one of our papers, and many other papers have been doing this over the last decades, and there's a selection of some of them at the bottom of the slide, but there are many more, I know, is to look at absorption features in galaxies and model those through stellar populations, and then derive, of course, ages of stellar populations, metallicity of stellar population, but also now we have become quite good at looking at some individual chemical elements, what I was describing before, that tell us about the formation histories. And this is really looking at various absorption features, but the field has moved on quite considerably over the last 10 years or so. And most people are now doing full spectral fitting. Maybe if I go just back to this, once, you can see in blue is some of the papers that have been doing this to get element abundances, but actually there was some revival of this method of looking at the absorption features directly when people were looking at the IMF variation in particular. So there is quite a bit more recent work that is also just using absorption features again. But apart from this, there's a lot of work in full spectral fitting, and these are some of the codes that are on the market. And again, there will be many more that are being used in order to fit the theoretical spectrum of a stellar population to the observed ones. And I think these two figures I want to show here are a moment of, I think, glory of the field. We are really down, if you think about it, precision astrophysics, of being able to recover all these details in the features of a spectrum of a galaxy, I think is quite a success. Having said that, of course, there's still a lot of problems then in the parameters we derive because of all the degeneracies that I mentioned before. It is still a very hard undertaking. Oh, before I come to that comparison, I want to say really what we want to achieve, and that's where full spectral fitting has come in improving that, is to try to dissect the entire star formation history. So that's something that the VESPA code quite a while ago has started off, and many of the other codes I just showed on the previous slides are doing this routinely now, trying to derive the star formation history without parameterizing it before. And you can see a successful case here of a quiescent galaxy, star forming galaxy, the spectra are fit, and you kind of get formation histories that resemble these kinds of what you would expect from a star forming galaxy to have some residual star formation at later times. And so now when you compare the different codes, Charlie Conroy has done this in this paper from 2014 in quite a detail. And I think there's good news and bad news. If you look at this, you can see that there's quite an agreement, for instance, this alpha to iron ratio, which you can also say is magnesium to iron ratio. Actually, that there is this relationship, as I said, was actually quite stable over the decades now. Everybody really agrees that Mg to Fe ratio in galaxies scales with velocity dispersion or the mass, and this was the downsizing pattern I was describing in the beginning. But of course, when you look at the detail, there's quite a bit of offsets here. What is the exact level of this alpha enhancement, as it's called? There's quite a good agreement about more massive galaxies being older, as you can see on the left-hand side. But other things, for instance, how you treat iron abundance, you can see that now suddenly the codes are giving you quite different prescriptions, and there's a lot about what kind of assumptions you make and how you're actually dealing with varying element ratios in your models. And you can see that our work is the blue one, suggests that actually iron abundance doesn't change when you increase galaxy mass. And while other work show there is still a substantial variation. So this is, for instance, one of the things we really need to pin down if we want to get a grip on the physics of galaxy formation. And I want to just briefly share with you some exercise we did in the Sloan Digital Sky survey, where we asked several groups to derive ages and metallicities of these 4 galaxies from SDSS. And we were comparing them. And I just show you some of those. This is the light average age that we derived. The median shows you that this galaxy on the right is the youngest one, star forming, and a passive galaxy on the left hand side, and there's a clear correlation. Now the codes actually quite agree on this trend, but there is a lot of scatter, as you can see, when it comes to those. And metallicity, again, the star forming one is actually more metal poor, and this time when you look at the codes, there's a huge discrepancy. So this is a really simple exercise. You give a group of, or a set of groups, the same spectrum, they derive age and metallicity, and that's what you get. So I think this shows you that we are still, you still have to learn a lot, and still look at our methods and our theory to really get a good grip on these parameters and understand stellar populations in galaxies. And something really important I also want to mention briefly is something that has become more and more possible with full spectral fitting, where you look at, you use more information, you have more information of comparing the mass average with the light average. So you can look at how does my metallicity look like when I give weight by light of stars. Then obviously the young stars and the metal poor stars will contribute more, or you could look at it by mass. In which case you are looking at the more physical quantity, because that really tells you when the main star formation episode was. And if you look at the age, you can do that light average or mass average. Again, there's quite a bit of scatter. That's the difference between the light and the mass average. You can see these are negative numbers. So your light average is always younger than your mass average. So that's exactly what you would expect. So they all agree on this, but there is, again, quite a bit of scatter of the detail. But what is really interesting when it comes to the metallicity, and there is actually really a difference. The blue line is the code Firefly that we have developed in Portsmouth, and you can see that our results are suggesting that the light average tends to be higher metallicity than the mass average. And in our mind, that makes a lot of sense, because the younger stars, if you look at it chemically consistent, they should be more metal rich. And because the younger stars, they are brighter, they contribute more to the light average, you should be getting higher metallicity when you look at the light rather than the mass average. And so we think it makes sense what we find there, but you can see that many other codes find exactly the opposite. So again, there's a lot of really important detail, I think, that we need to iron out and talk about. So let me move on and tell you a little bit about some of the science that we have been doing. And in Portsmouth in particular, we've been working quite a lot, and I think many at this conference too, on the MaNGA survey in SDSS, which has given us now 10,000 galaxies, IFU measurements of 10,000 galaxies. And one of the things, of course, my slide is stuck a moment. Sorry, I wanted to move on to the next slide, but it doesn't do it. Can you still see me? I just
we see you, but not the slides.
Yeah, I stopped sharing because the slide was stuck. So hopefully, if I go back to it, hopefully it comes back. Okay, I think that's fine now. Somehow oh yeah, okay. Anyway, sorry for that. So one of the good things about these large surveys is that they give us a good handle of the environment. And when it comes to the physics of galaxy formation that we want to understand, it's a lot about how does the environment affect the formation of galaxies, because obviously there's a lot of predictions in hierarchical clustering that you can make in this regard. And I look forward to, there's lots of talks at this conference about this. But Anna, I think, is talking today, and to James later in the week about the effect of environment on galaxy formation. So back to MaNGA, of course, this was pioneered by surveys such as Sauron, Atlas 3D, and then Khalifa more recently, of doing IFU observations of galaxies. And what MaNGA has done now is to up the game to 10,000 galaxies. But of course, what this shows you get a lot of detail about how stellar populations are distributed in galaxies, and you can connect it to the kinematics. So there's a lot to learn about the physical processes. And yeah, as I just said, MaNGA reached the milestones. In fact, the observations are finished, not the project overall, because we still have to release and prepare the final data release. But the observations are done. 10,000 galaxies, a bit more than that, are in the box. So that's a great achievement of this team, really. Something, before I come to the science, I want to mention what MaNGA has been doing, and I think many of the other surveys are experiencing as well. And that's maybe something we need to discuss at this kind of conference too, when it comes to the future, is to think about how to disseminate data. And in particular, complex data such as IFU data are really, really difficult to present on the web. And there's a web interface, Marvin, that is being developed by the MaNGA team, which I think is quite powerful. So just to flag this up as something that we need to think about as well when we design these future experiments. What the Marvin does really nicely, you can see the IFU footprint, and you can actually click. Now this is just on the slide, but you can click anywhere in that image, and you get the spectrum with a fit, and then you get some maps. So that's really, really handy when you want to have some first idea about how your data look like. And another thing, of course, with these huge data volumes is what we do in SDSS for a long time already is value-added catalogs with additional information. There's many for MaNGA, also by many of those here present at the conference. This is the one we've been producing in Portsmouth, led by Justus Neumann, and he's going to talk a little later in the week, and he might mention a little bit of this as well. Another spin-off actually that we achieved from this survey is that we took spectra of stars, not just galaxies, and were able to construct a new stellar library, which when you interpret SDSS data, is handy because it's the same instrument, but it's also extremely powerful because you get a huge wavelength coverage. It's the SDSS wavelength coverage, the entire optical that CCD cameras allow, for a huge amount of stars, over 20,000 stars in the Milky Way. And we have been now working hard over the last years of constructing this library and making stellar population models. And you can see this here. And this is a globular cluster spectrum that Louis Hill, student of ours in Portsmouth, has been leading. And that's the fit we've done before, based on Claudia Marston's models with Miele's library, and now with these new models. I think it's an incredibly beautiful fit, and you can see how nicely we cover the full wavelength range. And the models are also out on the webpage, and just to show that because of the vast number of stars, we also have a good coverage of stellar parameters, and can cover very low metallicity and very young ages in these models as well. Okay, so then a few slides on some of the science that we have been doing. One of the things I really like about what this kind of data allowed us to do, and I think it's being done a little bit more, even though I think really this kind of investigation doesn't quite yet get the attention it should, which is comparing metallicities, in particular element abundances, for the gas in galaxies and the stars in galaxies. And these are actually stacked maps where you can see the gas metallicity and the stellar metallicity for different mass spins, increasing from left to right. And well, there's a lot of stuff in there that I really can't go into. The main message really that I want to show you, you can see the gas is much redder. It's the same color scheme. So you can see metallicity in the gas is much higher than it is in the stars. And you can also see that the gradient in the galaxies is very different. And we have produced chemical evolution models. Jian Hui Lian, who was a postdoc in Portsmouth, has been leading this stellar population chemical evolution models to model exactly that kind of behavior. And it turns out it's really difficult to get stars, an average metallicity in the stars to be significantly lower than in the gas. It makes a lot of sense as to physically, but then the numbers turned out to be quite challenging. And actually in this modeling, we found there's quite a lot of consequence for the physics of galaxy formation, in the sense that galaxies have to lose quite a lot of metals at early times in order to keep the metallicity average low in the stellar population. So that's one of the results, and I think it's going to be exciting in future to see how this plays out in actually full cosmological models. Thank you, Claudia. And another study we've done that we can do very nicely with MaNGA is to look at the stellar initial mass function. Again, this is an entire own talk, so I'm not going to say much about it. Tanya is actually showing a poster. I don't know whether exactly about this, but some related topics. So you can have a look at that. And so Tanya Parek has been doing this as a PhD student with us in Portsmouth, and we have been able to stack spectra, get very high singleton noise, and measure, and then the variation of the slope of the stellar initial mass function, and that variation within galaxies. So look at the radial gradients, and let me let me show you this. So this is one of the this change in slope of the stellar mass function is shown by a mass excess factor. And you can see that relation with galaxy velocity dispersion that is found in the literature. And what we are showing here, our results are these colored circles there, that actually the gradient in galaxies is even steeper. So there's even locally in galaxies, there seems to be even more of an effect of variation of IMF if the whole diagnostic is true, but I can't really go into that question in this talk today. But if that effect is true, then it seems to be even stronger within galaxies than globally. And what we find, and other people have seen this too, and maybe Ignacio will talk about this in his talk later today, or this week, I don't remember whether it was today, that it seems like metallicity is very much driving all this variation of the stellar initial mass function. So I now have just a few minutes left, so let me come to just some future aspects. One of the things I think really we have to do when we do stellar population analysis, and some of this is on the way, of course, already, is to really push as far out as we can in galaxies into the halos of galaxies. And we are looking at 1.5 effective radii in MaNGA and many other IFU surveys. We really have to push this, and there's some individual observations of individual galaxies already out there, of course, where this is done. But in order to do this at large scales, we really need to push our instrumentation to tap into the halos of 3 or 4 effective radii to learn much more about the assembly of galaxies. And of course, high redshift is very important. Claudia said in the beginning, I was given more time to include redshift, so I'm a bit embarrassed that it's only really this slide here at the end. And really what I want to say here is, and again, we have some talks coming up later today or just after me, so I'm sure we will hear much more about studies of stellar populations at higher redshift. And what I want to say, some of the studies that do very similar things of what I have been describing locally now at higher redshift, and there are some of these here on the slide, are finding very similar results. That's why I say passive means passive. It looks like, in particular, this alpha enhancement that I have been mentioning, that we use as a signature for downsizing, is already in place at very high or relatively high redshift. That's about as far as experiments could push it so far, but the future is bright, and that's certainly something we are discussing this week, and where we can do this much better in future instrumentation and telescopes. So up to around redshift 2, we can see that galaxies are still, and these are the, here you can see alpha to iron ratio as a function of sigma, and the same for the Creek et al. Paper, the top panel. So these ratios are still low, and this relationship seems to be already in place at very high redshift. There is some differences. Of course, galaxies are younger. That makes a lot of sense, but also they seem to be a bit more metal poor. So that's quite interesting, and actually suggests that there might be some additional information mechanisms still going on since then. So I think the data quality, of course, isn't quite there yet for high redshift, but it's something really, really important that we have to push the field to get detailed stellar population analysis of high redshift galaxies to better quality than we have today. And another strand, I think, for the future, we really have to up the game, and there's a lot of work on it already. Lorenzo Nani, one of our PhD students in Portsmouth, is working on this, but I know that many are doing this already in the literature, is to actually do mock galaxies through hydrodynamical simulations and do a really proper comparison between what theory predicts. So treat your theory just like the observations, and then make very direct comparisons. So I think that's an important part of where the field is already moving, and that will be an important part in learning about the physics of galaxy formation. So I'm through. I just put up my summary slide here and stop here so that we have some time for questions. So thank you very much.